Hi. So this video lesson is going to be about our different types of friction and how we can numerically calculate for friction in order to be able to help us determine rates of acceleration, determine weights of objects, and how we can get objects to accelerate based on the amount of friction that's present. So to begin, we're going to look at our two primary types of friction. We have static friction and we have kinetic friction. The word static helps us identify that this means that the object is at rest, which is important because in our free body diagrams, remember when we draw those, if an object is at rest or if an object is at a constant speed, right, if it's moving at a constant speed, all of our forces are going to be balanced. So what this automatically tells us here about static friction, because the object is at rest, this is the amount of friction that is generated against the pushing or pulling of an object before it begins to move. So if you push something with 50 newtons of force and it doesn't move, that means static friction is acting in the opposite direction at 50 newtons of force. If you push with 5,000 newtons of force and the object doesn't move, then static friction is working against you at 5,000 newtons of force. The forces are still going to balance out, but now because we know it's static friction, we know the object is not in motion. So the applied force and that static friction have to be the same. And the static friction, like the example that I was giving, will continue to increase and increase and increase up until some maximum value, which is determined based on the two materials that are in contact with one another. Once you get past that maximum value, the object will then break free and begin to move. And as long as it's moving at a constant speed, we're going to see our kinetic friction matching our applied force. And so our kinetic friction, the word kinetic, again, helping us here, motion is our big term here. You need to overcome kinetic friction for this object to continue to be in motion. And the difference between static and kinetic friction is static is going to increase, and that's going to be a variable number up until a certain point. Once that object starts moving, the kinetic friction does not change. So if you apply a force greater than the kinetic friction, now the object's accelerating. And if you apply a force less than the kinetic friction, it is still going to be in motion, but now it's going to be slowing down. And if you apply a force equivalent to our kinetic friction, then we're going to be moving at a constant speed. Our kinetic friction, once it gets moving, is always going to be less than the maximum amount of static friction. If you picture pushing or pulling any object, it's always harder to get it started than it is to keep it in motion. Think law of inertia here. If an object is at rest, it wants to stay at rest. If an object is in motion, it wants to stay in motion unless acted upon by an unbalanced force. Well, if the object is already in motion, it takes less force to keep it in motion than it does force to get an object to start in motion. So as we overcome friction, this graph helps diagram that idea. So on the vertical axis, we see our resistance force, and on the horizontal axis, we see the applied force that is generated here. So there's a linear relationship between the amount of resistance and the force that we apply up until we get to that threshold of motion, which is that vertical dotted line. So if you apply 10 newtons of force, the resistance is 10 newtons. If you apply 20, the resistance is 20, up until whatever that threshold is. If you apply more force than what that threshold happens to be based on the two materials that are in contact, then the amount of force that you apply can continue to increase, but the amount of resistance against you stays constant. So kinetic friction will always apply a constant resistive force versus your static friction, which will apply a variable force up until some maximum. And if you see that point at that threshold of motion, that point is going to be the maximum amount of static friction that is generated. Anything after that, notice that flat line, our kinetic friction, our resistance, stays constant, does not change no matter how much force is applied. So if you apply way more force in the amount of kinetic friction, you're going to get a larger acceleration. If you apply an equal amount of force to the kinetic friction, you get zero acceleration. And as we calculate this friction force, it really comes down to two things. How heavy is the object, and what are the objects that are in contact? because if you put a plastic sled on snow and have that plastic sled slide across the snow, it's going to be far different than that plastic sled going across grass or going across concrete or going across asphalt. If you similar example, if you take a tire and you try to push a tire on ice versus pushing a tire on concrete, you get two very different responses, even though the weight of the object stayed the same. Because the surface has changed, the amount of friction between them is going to be different. Now recall, our weight is F sub g, or mass times gravity, right? Mass times the acceleration due to gravity, I should say. And each pair is going to have what's known as a coefficient of friction. So this coefficient, the way that we see it, it's a ratio between how much friction is present divided by how much weight there is, right? So the weight of the object and how much friction is generated. When we divide those two out, because it's a ratio, so that's what we're going to do, the unit drops. So this coefficient gives us the relationship between frictional forces and the weight of the object. And because we're ratioing forces, there is no unit. This is not labeled newtons. It's not labeled newtons per meter or newtons per newton, right? It is a unitless number. So for example, let's say the coefficient of friction between these two materials is 0.5, or the coefficient of friction between these two materials is 1.2. There's no unit that's going to be present there. And this Greek letter mu, the u with like the little addition there on the front, that's how we're going to symbolize this. So mu sub s is going to be static friction. Mu sub k is going to be our kinetic friction. And we see that here. So our static friction, which again reaches some maximum value, is going to be divided by the weight of our object, and that's going to get us our coefficient of static friction. Our kinetic friction, we can find it the exact same way, where we have our coefficient of kinetic friction, mu sub k, is equivalent to the kinetic friction force divided by the weight of the object. And remember, weight can also be mass times the acceleration due to gravity. So keep in mind, your kinetic friction force is going to be constant. Your static friction, we're always looking at the maximum value. Typically, that's what you're going to be given, is that maximum. Notice here, we're force divided by force, so that unit drops, which is why the coefficient does not have a unit at all. We're newtons divided by newtons here, which cancels out. The form for each of these is the exact same, because the coefficients are telling you the same piece of information. It's just, are we talking about when it's in motion, which would be kinetic, or when it's not in motion, which would be static? And what the coefficient tells us is how slick these objects are, right? How slippery it is when they're in contact with each other. So if you have a very high value for a coefficient, something that's greater than 1, means that those two materials are going to be very, very sticky. There's going to be a high amount of friction generated when you go to push these when you go to push the two objects. If your mu value is less than 1, that means that it's really easy to slide it, because the two surfaces are going to be relatively slick when placed next to each other. It comes down, and because that ratio deals with force, really, if your frictional force matches your weight, that means the amount of force it would take you to slide it is going to match the amount of force it would take you to lift it, because that friction force equals the weight. If that number is greater than 1, it's going to require a lot more force to push the object than it would to lift it. And if it's less than 1, it's going to be far easier to push it than lift it. So thinking about materials where this happens, right? Like high friction surfaces that we have. So looking at this example, rubber on concrete. If you take a rubber sole on your shoes and you go out to a nice hardwood basketball floor, there's a lot of friction there, because the goal is for the shoe to not slide. So there's a lot of friction there. And on this table, as you look down that table, we notice our static friction numbers start decreasing and our kinetic friction numbers decrease as well, all the way to the point where we see ice on ice at the bottom, which is really slick. And if you think what's happening, if you were to take a chunk of ice and slide an ice cube across a sheet of ice, it's going to take a really long time for that for that ice cube to stop moving because the coefficient of friction between those two materials is so low. It generates such a small amount of friction, it takes a long time for that ice chunk to stop. Compare that to having like a rubber tire on concrete. If you put a rubber tire on its side and then try to push it, it stops really quickly as it attempts to slide because it grips it. There's such a high amount of friction there that it does not allow the object to carry very far because of the amount of friction that it generates. And our ways that we can get around friction, and in the bottom right-hand picture we see it. We have two kind of turquoisey materials. If we place an oil in between them or any sort of lubricant, that's going to substantially decrease the amount of friction that is generated because friction generates heat. It generates that thermal energy, which can be very, very damaging. Looking again at the table here, you see steel on steel towards the top with 0.74 for a coefficient of static friction and 0.57 for a coefficient of kinetic friction. Aluminum on steel, 0.61 and 0.47 respectively. So those are a metal on a metal, and that's unlubricated. And the general trend that we will always see is that the static coefficient is going to be higher than the kinetic coefficient because that static force will be greater than that kinetic friction force. But when we take metal on metal and it's lubricated, now look at that coefficient of static friction at 0.15, substantially lower than 0.61 and 0.74 that we see above. And then the coefficient of kinetic friction down to 0.06, which is far less than the 0.47 and 0.57 we see for the various metals up above. So simply adding that lubricant substantially diminishes the amount of friction that we experience, which is going to make the movement more efficient. Right? It's going to make that sliding way, way, way more efficient based on having that little bit of oil in there. So that is what we have for friction, right? Being able to calculate it, being able to conceptualize it, and being able to understand that we have a difference between what happens for friction when we're not in motion versus what happens with friction when we are in motion.